Hey there, welcome back to another Explainer. Today we are absolutely diving into what I think is a real core puzzle of physics. We're going to look at how objects move, and maybe more importantly, how they manage to stay perfectly balanced. Now I know it sounds super basic, but the physics of balance actually holds some pretty incredible surprises.
Okay, let's dive right into this. We'll start with the basics of velocity, then define static equilibrium, move on to dynamic equilibrium, and finally compare the two side by side.
So, Part 1. The basics of velocity.
Just as a super quick refresher, before we really get into the weeds of equilibrium, we generally split velocity into two distinct camps. You've got translational velocity, which is basically movement along a straight or curving path. And then you've got rotational velocity, which is moving continuously in a cyclic or a circular path.
We literally see translational velocity everywhere in our daily lives. Think about a car just cruising down a highway, right? Or an airplane flying its direct flight path, or even the curved trajectory of a cricket ball soaring through the air. Basically, it's anything moving from point A to point B.
Then, on the flip side, rotational velocity is all about cyclic motion. It's the Earth orbiting the Sun, or just the hands of a clock ticking away on a wall. They aren't traveling from point A to point B. They're locked in this continuous circular loop.
Moving right along to Section 2. Defining static equilibrium.
Okay, here's our formal definition. Static equilibrium is a state where a stationary body has absolutely zero translational and zero rotational velocity plus zero net force acting upon it. The absolutely crucial word here is stationary. I mean, literally nothing is moving.
The underlying math for this is actually pretty straightforward. Velocity is zero, meaning there's absolutely no speeding up or slowing down. So, by default, acceleration is zero. And thanks to Newton's second law, which connects force and acceleration, a zero acceleration dictates that the net force simply has to be exactly zero.
And this brilliantly illustrates the concept in action. Think of that giant, heavy textbook you've been maybe kind of avoiding, just resting flat on a table. It's not moving at all, but the forces are highly active. Gravity is pulling it down, while the table is pushing back up with an equal normal force. That third step is really where the magic happens. Those opposing forces balance out perfectly to net zero.
We see the exact same thing happening with a hanging light bulb. You've got that downward gravitational pull, which is perfectly countered by the upward tension from the wire. Because the bulb is completely still, those opposing forces guarantee that the net force is, once again, a big fat zero. But this brings us to a really fascinating question, one that kind of messes with our intuition a bit. Does equilibrium actually mean an object has to be completely still? Like, does perfect balance only exist when all motion stops?
Let's find out in Section 3, Defining Dynamic Equilibrium.
So here's the counterintuitive part. Dynamic equilibrium is a state where a body is actively moving with a constant velocity, yet, and this is wild, it still maintains zero acceleration and zero net force. Movement actually exists, but the net force is miraculously still zero.
Now, what's really interesting here is that mathematically, these conditions are nearly identical to static equilibrium. Because the velocity is constant, meaning it never speeds up, it never slows down, it never turns, the acceleration is zero. And once again, Newton's second law steps right in. Zero acceleration means zero net force. Literally, the only difference is that velocity is a constant number instead of zero.
Imagine a car driving down a perfectly straight road at a uniform 40 meters per second. Because that speed is completely unchanging, the acceleration is strictly zero. So therefore, despite literally flying down the highway, the total net force on that car is zero. It is in perfect dynamic equilibrium.
And hey, let's scale this up to the macro level to really put it in perspective. 30,000 meters per second. That is the staggering, uniform velocity at which the Earth moves in its orbit around the Sun. Because that rotational velocity remains essentially constant, the acceleration is zero, making the net force zero. Basically, our entire planet is hurtling through space right now in a massive state of dynamic equilibrium. How cool is that?
All right, let's bring it all together in Section 4, Static versus Dynamic Compared.
So, the absolutely crucial point here is understanding the key differences between these two states. The defining difference is entirely about velocity. In static equilibrium, velocity is completely 100% zero. But in dynamic equilibrium, velocity is a constant, non-zero number. But I want you to notice those bottom two metrics, the zero acceleration and the zero net force.
That rule perfectly unites both states. Whether you are sitting perfectly still or moving at a constant speed, the total forces acting upon you balance out to absolute zero. In the eyes of physics, moving at a constant, unchanging speed is mechanically indistinguishable from standing perfectly still.
So I'm going to leave you with this provocative thought as we wrap up today's explainer. As you sit there watching this, I want you to think about the forces acting on you right this very second. You've got gravity pulling you down, right? You've got the normal force from your chair pushing back up, and you've got the rotation of the Earth literally carrying you at thousands of meters per second. So based on the differences we just covered, are you in static or dynamic equilibrium? Ponder that for a bit. Thanks so much for joining me. Keep questioning the forces around you, and I'll catch you in the next one.